Okay, so we're going to look at the 8.4 notes in the first part right here. I've already made a video, but unfortunately it didn't have any sound, so I'm going to remake it. It's already got the stuff written, so you may need to pause me to keep up with the writing since I'll be talking and not writing at the same time. So what we're focusing on in 8.4 here are introducing polar coordinates and polar graphs. Some of our objectives are we're going to graph points given their polar coordinates. We're going to convert between rectangular coordinates and polar coordinates and vice versa. And we're going to also convert rectangular equations to polar equations and vice versa. We're also going to graph some polar equations. Okay, so warming up. The standard XYZ coordinate system is the coordinate system that we're used to. Usually we talk about X and Y if we're talking about two-dimensional space, and XYZ if we're talking about three-dimensional space. So we can see our two-dimensional space as an XY grid, or a three-dimensional space as an XYZ, and that would be where the Z-axis, even though we draw it on flat paper coming out, the Z-axis is really standing straight up because, again, three-dimensional space is the space we live in. Okay, so we can use these types of measurements to define where a point is. And we'll talk first specifically about the 2D case because that's what we're going to work with in the polar is the 2D case. So in the 2D case, we could, if we wanted to figure out where a fly was located in the classroom, for example, we could say, well, if this is the center of the classroom, maybe that's where you're sitting, you could say, well, if you walk X paces to the right and Y paces up, you can see where the fly is. However, it may be more useful instead if you're sitting at that same place just to lift your arm and point at it. And if you point at that fly, if it's in the same place, instead of it being located at X, Y, where it's X paces over, Y paces up, you could say it's at an angle of theta and out about R paces. And so there are some cases where polar coordinates make more sense. So pointing at something, or if you're talking about locating a ship, like we're talking about direction as well, or direction of a constellation, anything that describes an image or a slice like this is going to be something that may be better represented in polar. That's what we want to talk about in this section, is our polar coordinate system. Okay, so polar coordinates are another system for locating things in space, just like the rectangular coordinates. We're starting with a two-dimensional space, i.e. the XY plane, but we're going to locate things based on an arc and an angle instead of on position left, right, and up, down. Okay, so the origin point is the center of the coordinate system, just like it is for rectangular coordinates. It's also referred to as the pole if we're talking about it in polar, but it is the ordered pair 0, 0. So the pole, or the origin, is the ordered pair 0, 0. We don't use the word pole in rectangular coordinates. That may be a new word. And then angles are measured up, counterclockwise from center, just like they usually are in the unit circle. So we're measuring them up from center and from the positive x-axis, or the line y equals 0. Okay, so just like we normally measure angles in the unit circle. Now, plotting points on a polar graph. So this is what a polar grid might look like. We can talk about all these points in a moment. But a polar grid is usually a bunch of concentric circles that have various r values and angles. And we can even label a few of these angles going around just to figure out what they are. But our polar graphs have that grid of concentric circles instead of a grid of boxes like rectangular coordinates. We mark off specific angles, and anyway, the polar coordinate systems are in the 2D plane are stated in the form of r comma theta. There we go, r comma theta. So instead of x comma y, we list the r value first, then the theta value second in our ordered pairs. So to graph these, we're going to locate the angle theta, and we're going to measure the angle from the positive x-axis, and then we're going to move our units. Now, r can be either positive or negative. So if r is positive, we're going to move outward along the directed angle. So if you have a positive angle, you're moving positive direction, your r value is going to be out towards it. But if r is negative, instead of going out towards the angle, you're going to go backwards on the other portion of it. So you're going to go in the opposite direction of the directed angle if you have a negative r value. Okay, so let's take a look at some of these points right here and getting them graphed. So the first one we had Well, the first thing I would do actually is, and something I didn't do last time, is take a second to label some of these angles. So if I count them, I have 1, 2, 3, 4, 5, 6 slices before I get to pi halves. So that's pi halves up here. So a sixth of a half is a 12th. So each of these is a 12th. So I have pi 12ths, pi sixths, etc. 3 pi 12ths, which is the angle. Oh, I don't need to write 3 pi 12ths. I could have just written pi fourths. I was going to reduce it first. So pi 12ths. And then 4 pi 12ths, which reduces to pi thirds, and then 5 pi 12ths. So I don't need to label all of them all the way around, but it is useful to know what the measurement here is. So it's more than the unit circle measures, partially because the unit circle only lists the values for pi sixths, here, this is pi fourths. I was trying to write my 3 pi 12ths right there, which is the same thing as pi fourths. On the unit circle, you normally only see the angles for pi sixths, pi fourths, and pi thirds. But because they're not equally spaced away from the x-axis and y-axis as they are from each other, we want to have pi sixths be the increment, because then every single increment is equally spaced. If that makes sense. So we're using pi 12ths for the increment here. Okay, then of course down here we have 0, which is also 2 pi. Okay, so taking a look at a few of these, the first angle, 60 degrees, which corresponds to pi thirds, and we went 3 up. So from the center on the third concentric circle, that's our point A. 45 degrees, that's the same thing as pi fourths, and we're at 0. So actually, we're right there at the origin point, and so it doesn't actually matter what the angle is. Anything that has a radius of 0 is going to be right there at the origin. Okay. Point C was up at the angle 120, but instead of being on 120, we reflected across because the angle was negative. So we kind of backwards 5 around the 5th concentric circle, but in the negative direction. That's our point C. Point D, the angle was negative 60, so this is the angle, but we have a negative 7 for the radius. So instead of being on the angle negative 60, we were reflected, and we're counting up 7 on its angle over here. We're going in the opposite direction. So it's on the 120 line, even though the angle was negative 60, because we reflected it across the negative radius. Point E, we're on the angle 3 pi halves, and we're down at a radius of 2, so we just follow straight. 3 pi halves is this angle right here. Count out 2 concentric circles. And then last, point F has an angle of pi thirds. So pi thirds is right here, and negative 10, so backwards negative 10 on the 10th concentric circle.